So I won't delay too much longer. I guess we'll get started. Yeah, so this is a video lecture to give a description about how we designed our feed system. We've got a couple of people here today in person. Yeah, this video is designed to show how we designed the feed system, and it's supposed to be a zero background knowledge kind of experience. Vanna, you're here in person, so please interrupt me if you have any questions about this. Definitely want to make this like as useful as possible for you. Hopefully, really build up confidence that like you don't have any further questions or something after that. So yeah, without further ado, let's just get started. So on the agenda for today, we have, I'm just going to go over a little bit about myself. Everyone here already knows that, but I'll go for it for the video. And I'll describe what a feed system is and the use of what's called piping and instrumentation diagrams is how we communicate process flow designs. And by the way, like a rocket engine is a process flow. Multiple processes happening, whether it's firing the engine or if it is filling propellants. And then I'll go over the 2023 test and design that was worked on by senior design and myself. So let's get started. So my name is Ryan St. Clair. I am a mechanical engineering student here at Rose-Hulman, graduating this year in 2023. I'm a student lead at Rose Propulsion Laboratory, and I own the design of the feed system for the senior design project. So if anyone has any questions watching this video, definitely feel free to reach out. I'm graduating this year, but I'll be happy to communicate and stay in the loop on this project as it grows bigger for the up and coming CPLC competition. So you can contact me through email, phone, or LinkedIn. Yeah. So I'm going to go over what is a feed system, like why, if you're, designing a rocket, you're kind of interested in this club, but you don't really know, what goes into a rocket engine. A feed system is a big part of that. So I'll kind of go over that. So how do rockets really work? So rockets make thrust. They go up into space because of a momentum conservation process. So you burn propellants into a combustion chamber, and those propellants get really hot and they produce a lot of pressure, which ultimately makes it shoot out of a nozzle at supersonic speeds, and it causes that rocket to be pushed the other way. Thinking about like, you're on a skateboard, you have a heavy bowling ball and you throw it the other way. Well, that's just happening with a lot of velocity and a lot of mass. So in order to do this, you need fuel and oxidizer to combust. Think about the fire triangle. Is very relevant here. You need some kind of fuel, some kind of like way of giving it oxygen, and of course the that energy to just make it start combusting. Also, this fuel and oxidizer needs to be pressurized. So if you're whatever pressure you're combusting your propellants at in your combustion chamber, you need to have a higher feed pressure than that combustion pressure, because you want fluid to go out of your from your tanks to your combustion chamber and then out through your nozzle. And in order to do that, like fluids flow from high pressure to low pressure. So you gotta ponder, how do you get that pressure or those propellants to be up to pressure at a higher pressure than the combustion chamber pressure? And there's a couple of ways that people do that. If you look at any like industry rocket, it'll tend to use turbopump systems. So basically you burn a little bit of propellant in what's called a preburner, and those drive turbines that spin pumps, and those pumps provide pressure to put the to get that propellant from the tank to the combustion chamber. Turbo machinery is a very complicated project, and you never see that happen on student teams. The more common way that you see that is by using what's called a pressure-fed cycle. So the pressure-fed engine cycle basically provides pressure just by using a pressurized gas. So you can imagine that This pressurized gas shown in blue has a regulator that is pushing that propellant down into the combustion chamber at whatever pressure that's being regulated to. And to kind of give more of a visual example of this, it's called a blowdown system for kind of this reason, that you have this pressurant that is pushing down and blowing down that propellant, again, at the same pressure that is being regulated to into the engine. So if you want that to be at, say, 600 psi for feed pressure to combust into a chamber that is being at a pressure of 300 psi, you get that 300 psi drop, and you would set your regulator for your pressurant to be at 600 psi. So now I want to talk about what are called piping and instrumentation diagrams. This is how we communicate process flow designs, and like I said, rocket engines, rot with processes for their fluids, whether it's when it's time to hot fire or when it's time to load propellants. Those are different processes that we want to be able to design and communicate very well. So P&IDs, the what and why. Piping and instrumentation diagrams, this is kind of the what. They show the physical relation between components in a process flow. So they can show different components and their position along process flow. So, what components are in your system? Is there like different valves or instrumentation or something that is somehow affecting the flow? They can tell what type of lines are used and where they are. They can show the pressures and temperatures for each process, at different steps along the way. So if you're opening a valve, then you're going from like maybe atmospheric pressure up to a certain like feed pressure, like 300 psi or something. And then you can also show what lines are being instrumented and how. So if you're interested in knowing the pressure of a certain line because it's safety critical, or you need to know the temperature of a certain line because it's critical for your filling process, that's what a P&ID can show. And we do this because it can help us show how a change in the placement or operation of components will affect a process. So how does adding a needle valve become advantageous or maybe disadvantageous for what we're trying to do, maybe for a process that we're trying to fill propellants? But that's kind of like what P&IDs are and why we use them. Any questions at that point? Cool. So here's some common components that are in a P&ID. So you have, I'll start with the tank, usually just be labeled with like what's in it. In this case, there's N2. This is a pressurant tank. And then going up the top, we got a ball valve. A ball valve is just a like hand valve. It's a on or off kind of valve where you say you want this fluid to flow from here to here, or you want this pressure to be the same across here and here. And again, these are hand valves, but they can also be what are called pneumatic ball valves. So you can have a line of pressurant going to a ball valve and use that pressurant to be able to turn on a ball valve remotely instead of having that being a hand or a manual process. So then next we got a needle valve. A needle valve precisely controls the flow through or across it. So you can imagine there's this valve, and it's kind of like a ball valve, except you can turn it a certain amount of times to get the amount of flow that you want. So these are these are manual valves. So and when you want to control the flow, like it's very fine. So it's got a lot of turns before you actually get it all the way open or closed. And yeah, we use needle valves often for precisely controlling that flow. Say, for example, if we don't want to introduce CO2, liquid CO2 all the way into atmosphere, and we want to just slowly trickle into the system for some reason, then we introduce a needle valve for that purpose. A check valve is a valve that only allows flow to happen one way. So the check valve has like a spring on it, and if you have higher pressure in the direction that it can flow, then it will allow that to flow that way. But if you get higher pressure in front of that directional arrow where it's going to flow, then the spring will block that from going backwards. So check valves are like one-way valves, or if you're an electrical engineer, it's kind of like a diode. Yeah.
Yeah. How quickly can those actuate? Like, if you you had a hard start or something, would the check valve be able to prevent that from going up your feed system? Or
that's a good question. So can a check valve prevent a hard start from backflowing into the feed system? I was actually just reading about that today, and I think it's contested right now, or depending on who you ask. We included one in our design because we thought better safe than sorry. We don't want it, physically it wouldn't make sense to have like a fuel line have that produce pressure if it were to like combust up the upstream, because there's no oxygen present, that fire triangle idea. And then like, can a check valve even like react fast enough to prevent a hard start like that? Say if there was like fuel and oxidizer in one line theoretically, could that prevent that combustion from going backwards? And people say no. But again, this was when we were designing our feed system, there's a lot of things that we kind of overlooked, and we just included the extra valve in there. Whether or not it worked, we were just kind of a little bit more confident in case it would have been consequential if we didn't have that. So yeah, check valve, it does have some time delay for reacting. But yeah, now we have a solenoid valve. So a solenoid valve is another way, just like a pneumatic ball valve, to control the flow in your process using a solenoid. So this is a remote process. And so for our feed system, we use solenoid valves, and the problem that we're running into is that they heat up very, very quickly. So we're sure to only actuate those for a certain amount of time. We try to keep them on less than 30 seconds because otherwise they start to cook themselves from the inside. And I'll talk a little bit more about this, but my recommendation is that that the team moves on from solenoid valves to pneumatic ball valves. Then there's different ways of instrumenting a system. You'll see pressure gauges. So these are like the graduated kind of gauges that you see as a dial gauge. It doesn't have any like electrical readout. It's just like a manual readout that you look at visually. That's different from the pressure transducer, which is an electronic instrument that you use to connect up to your data acquisition system, and it reads out a certain voltage depending on what pressure it's reading. Basically, like, you can create a calibration curve where you say, okay, it's producing this voltage at 100 psi and it's producing this voltage at 600 psi. That'll be a linear curve between those 2 points, and you can linearly interpolate what pressure you're reading at what voltage that it's reading out. And then you have a thermocouple. This is like a temperature sensor, and there's different types. I'm not too familiar with the different types. There's like K types and T types, but they all have their different attributes, different ranges. Important to note that with any of these sensors, there's always going to be some kind of sensor delay between what actually happened and when you read it. So, and this is especially the case for like a thermocouple where it's reading temperature, but it only reacts so fast because it only has so much time for that thermocouple to actually heat up, and only so much time for that heat transfer process for like your fluid maybe you're trying to measure to actually transfer that heat to the thermocouple to get them to equal temperatures. Next is a pressure relief valve, and this is a safety device used to it basically kind of uses a spring to control the pressure that you see inside the I guess whatever pressure that is reading. So if you don't want it to rise above like 800 psi in your system, then you would put this pressure relief valve. It would be 800 psi, and when it goes off, it will relieve that pressure. They're also called pop valves, and the pop valves specifically react very quickly to those kind of changes. So if it's above 800, it'll pop off and relieve that pressure. You'll notice, kind of a small side note, I drew like all of these except for the pressure relief valve because we don't use a pressure relief valve in our system. They're kind of we found them to be more costly to implement, a less reusable but more cheaper way that we regulate or keep the pressure down at a safe level in our system is by using what are called rupture discs or burst discs. And burst discs, they're basically these thin pieces of metal that you include on your feed system inside a what's called a safety head, and it clasps down on it, and that little thin sheet of metal is designed to burst or rupture at a very specific pressure. And so as a result, they're like $50 each. Kind of an engineered product, and yeah, our feed system uses a 1500 psi burst disc because our next weakest component will fail at 1800 psi. So it's cheaper to have a rupture disc fail than like a tank or something, and safer, not to mention. And when this rupture disc does burst, it will relieve a lot of pressure very quickly because you're essentially just opening the line to the atmosphere. Next up is a particulate filter. So this is just like a black box with like some dots on it. And particulate filters do exactly that. They filter out particulates in the system. It's important to do that because when you have a high pressure oxidizer environment, you do not want to introduce any possible organic contaminants into the system because they can act as little pieces of fuel distributed inside your oxidizer system. And that's essentially the same as having, your fuel and oxidizer being the same line, which is you wouldn't want to do that because you can't get premature ignition in the feed system. So we are sure to filter out any particulates in the system at multiple places. Next up is a back pressure regulator. Back pressure regulator controls the pressure of the feed system, kind of like a pressure relief valve, but they're meant to be used more nominally. And by that, I mean pressure relief valves are not meant to be used over and over. They're not meant to regulate pressure per se. They're meant to be more of a safety device. Back pressure regulators are meant to be more used like nominally. So they're meant for repeated operation, and they control the upstream pressure, which is different from the pressure regulator, which controls downstream pressure. So a pressure regulator, this is kind of like what most people are familiar with, is where you have like a feed pressure that is maybe like 2400 psi, and you only want 800 psi across it. So you set it to 800 psi, and that's what it regulates. So it regulates downstream pressure, but back pressure regulator, again, regulates upstream pressure. So if you want your system to be at a certain pressure, you can get that same effect by having that pressure drop be across like atmosphere or something. So if you can set it to 600 psi, and then it will maintain that 600 psi. So those are some common components. I'm going to go over an example P&ID from University of Southern California's Liquid Propulsion Laboratory. This is credited to John Targonski's. We basically, how we made our P&ID for our system was a lot of it was modeled and take inspiration from this one. So kind of to, it kind of looks complicated at the start, but I found with P&IDs, like it's really like, you never do shake that like complicated, what am I looking at? It just takes step by step reading through it to really understand it. So what we have here is a blowdown system again. You can see there's this kerosene tank, and if you look upstream of that, there's these gaseous nitrogen tanks. So we can see that is going through, is being read by this pressure gauge. It's going across a particulate filter. There's like some electronic instrumentation. Then there's a regulator. It's, these tanks are typically tapped at like 2100, 2400 psi. So you don't always want that full pressure. So you regulate it down to a pressure that you want. Here's that pressure relief valve again. And it goes across this ball valve through a check valve. Obviously, they're concerned about some kind of backflow, and it goes through, again, this line. It looks like there's some flex hose that goes through, and here it arrives at this kerosene tank, and it just pushes that kerosene down through this line. They've got a flow meter right here. They've got a nice like legend. And then through that, across that flow meter, they have some kind of flex line here, a ball valve, which I imagine. Let's look at this. Okay, yeah, so they've got like solenoids going on. And then, yeah, basically it ends up in the chamber right there. And, where's the oxidizer? Because you need fuel and oxidizer. It looks like you follow this line up here. It looks like there's like gaseous oxygen tanks here. You've got particulate filters across each of them because, again, they're concerned about introducing a particulates into this high pressure oxidizer system. So they include these filters right here, and they go across here through this regulator. It looks like through a flow meter, again, check valve. And, if you take it step by step, you can really start to understand where how these systems are laid out. And you can also just start to understand like maybe some of their concerns when they're designing it. So like, why do they have these particulate filters here? It's because, again, they're concerned about that high pressure oxygen environment. They really want to make sure that there's no particulates along in there. Another interesting thing is like, oh, you've got like, gaseous nitrogen in here. So why would you have that going into your engine? Well, it's very likely that they want to purge their system of all atmospheric air. So they likely have this nitrogen tank here, again, across a regulator and a check valve here to make sure that this environment is completely clear of atmosphere and it's just a nitrogen-rich environment before they start to do their process of flowing gaseous oxygen. So with that, I'm going to go over the 2023 test stand feed system design. So this is not our rocket, this is the BD4, but I will open this up and yeah, basically kind of go through this step by step, just like I did with the other one. So to start off, we have gaseous nitrogen here, we have ethanol going on here, and we have like nitrous oxide here. So we've got 3 tanks that happen or that are in the loop basically when we're trying to test fire. We have this nitrogen like pressurant supply right here, the ethanol like intermediate run tank, and then there's these nitrous oxide intermediate run tank. And the reason we do that is because we only want to have a certain amount, or basically the exact amount of propellant that we need for this system during a hot fire next to an open flame at all times. So basically we cut off this nitrous oxide supply and this ethanol supply when we're ready to do the fire. We only use this for filling. Basically to kind of show the path of pressurant, again, we have this nitrous oxide or this nitrogen tank. This is a pressurant, and it wants to go through this regulator because, again, this is at 2100 psi. We don't want all that pressure. We only want to feed it at 600 psi, which we include some of this information around here, which is our targets. We're using fuel. For fuel, we're using ethanol. Our oxidizer is liquid nitrous oxide. We're shooting for an OF ratio of 4.5 to 1. That's another thing I should mention, that when you have these kind of rocket engines that you don't exactly, there's a specific ratio that you want for good combustion. You don't want 1-to-1 because if you just include the same amount of massive oxidizer as you have fuel, a combustion process really likes to use up a lot of oxidizer. So you typically have a lot more oxidizer happening in your combustion than fuel. The other thing is like that exact ratio to get all of your oxidizer to combust with all of your fuel. That's called the stoichiometric ratio, and the stoichiometric ratio produces the hottest flame, is the most reactive propellant combination, but it is, it produces a lot of wear on your system. It can make it very hot and can cause, your engine to melt. A lot of people that are designing these rocket engines are very concerned about reaching that stoichiometric ratio and making sure that they're just below that or only as high as they need on this OF ratio. So for example, alcohol with nitrous oxide has a stoichiometric ratio of 5-to-1, 5 units of massive oxidizer to 1 unit of massive fuel. And we're just below that with 4.5 because we are only planning to fire our rocket engine for about 4 seconds. So if you're designing a different engine, you can go for different OF ratios, and this is highly a factor of the pressure that's behind it and the geometry of the injector. So how much are you restricting the flow of the fuel to get more oxidizer out instead of fuel? So yeah, that was kind of a segue, but going through the path of pressure right here, nitrogen here is going across here into this regulator, and it reaches a particulate filter. That's just because our regulators come with particulate filters, so we thought it accurate to include that there. And then it goes through here, kind of across this flex line here, and it reaches this first control valve. So this is that solenoid valve that I was talking about before. Each of these solenoid valves are labeled. So this is solenoid valve 2. And when we want our full system to be pressurized, we open solenoid valve 2. And then again, all of these lines that are touching here, these are going to be pressurized to, what this pressure is regulating to. And yeah, so once we open solenoid valve 2, pressure is going to go everywhere before any valves that it reaches, but particularly it's going to go across this flex line here and enter this tank. And this is going to have fuel in it already. And when we're ready, solenoid valve 4 will open here, allowing the nitrogen to push this ethanol through this system, again, blocked by this ball valve here. And it's going to go through this system, enter this check valve. This is the conversation we were having before. Does a check valve, actually prevent backflow of like a back pressure event of combustion into the system? We included that anyway. So it goes across this check valve here and into the injector. So I guess one of the big questions that I would be asking right now is like, based upon where I've drawn, like, what is all this other stuff? So just to kind of clear that out of the way. Again, I think it'll be important to show the filling process to kind of demonstrate why some of these exist. So the filling process for ethanol here is we have a flask of ethanol. Think of like an Erlenmeyer flask with a stopper on top. And that's represented right here. And this Erlenmeyer flask has a certain amount of ethanol, way more than we need. And so we put this stopper on here, and the stopper has 2 holes. One of the holes feeds a dip tube, and the dip tube is basically just like a straw that goes and reaches down to the bottom of here. And that's what this line is connected to. The other hole for this stopper is just a hole for pressurant to enter. So we have pressurant entering into the system, and when we're ready to fill this this tank here, we'll open ball valve 2. And so now this will be the same at the same pressure. This will be closed, and then we'll also open one of the ball valves right here. So again, it's a little bit hard to follow, but you can see that there's no valves in the way of this line right here, and basically this line right here. So you can follow that across this flex line up here, across this T right here, this T right here. There's a T right there, and again, yeah, this is the same pressure. So the reason we have this ball valve open right here and this ball valve open right here, this one's a little bit more obvious to let ethanol through. But we have this one because we want to be able to bleed out the air out of our tank. Otherwise, we'll just start to, when we introduce pressure into this tank right here, that pressure will basically start to rise. And we want to kind of keep this at atmosphere. If we're just like introducing gas into a closed system, it's going to rise in pressure. So it's important to make sure that this is an open system and so that gas can escape out here. So then to kind of continue along here, when we're blowing, we're basically doing a blowdown system to feed propellant into here. So this pressure is starting to rise and it's blowing this ethanol through this dip tube, and then it enters through this ball valve and it starts to fill up in this tank. And again, there's nitrogen in here that wants to either build up pressure or escape out of this ball valve right here. So again, we open this ball valve, we get it to the line that we want, and then we close this ball valve and we close this ball valve, and now we have a tank full of ethanol. And so some of these other components on this ethanol side, you'll notice there's a pressure gauge here. and there's a pressure transducer here. So the question of like, why would you want to have both is because of dissimilar redundancy. You would like to be able to rely on your pressure transducer to feed to your computer to say what the pressure is at all times, but there's a chance that, you know, if that goes, if there's a wire that's disconnected or a wire that's burnt off or something, you know, how are you going to read the pressure? So it's important to have that backup pressure gauge. So if something goes wrong with your transducer, you can just read off the gauge and know what pressure your system's at. And that's important because I don't know about you, but like I would be afraid of knowing that there's a system that is at some kind of high pressure and you don't know what that pressure is. And it's like, is it rising? Is it falling? Is it safe to approach? So that's why we include these two gauges here. There's also a solenoid valve here, solenoid valve 6. That is basically a computerized way of being able to remotely release the pressure here. So if there's at any point we want to approach the system and remove the high pressure, we just click the solenoid valve on, and you know all of the gas basically within this system here will want to escape, and that's our remote way of doing that. That's also in addition, you've seen here our manual way of relieving pressure. So there's two methods. Again, that dissimilar redundancy is important. You'll recognize this component right here. This is our rupture disc, and it's designed to burst at 1500 psi. The next weakest component that we calculated was our tank would burst at 1800 psi. So again, this is a nice safety device that you know, it's all seeing the same pressure. So that's kind of why there's this like branch here, but you'll notice there's like no valves in between them. So all these components play a role in the same pressure. And yeah, basically, you know, I just kind of walked through all the components here. So it really is just like a step-by-step breaking it down, looking at what different components do and why they're there. You can really start to understand that with P&ID, and it also really shows the relation very well of like what lines are seeing the same pressure. So if you're familiar with like electrical engineering principles, like if you have a conductor that is going to different parts of your circuit, along that same conductor is seeing the same voltage. And that's kind of like the mindset that you have with this P&ID is like along, when it's never going across like a valve or something, you know, it's all the same like conductor or all the same lines. So they all see the same pressure, except when you, again, like open a valve like this, then you can start to separate those pressures. Now I'm going to go over to the nitrous oxide side and kind of show the path of pressurant. So again, you have nitrous oxide here, or sorry, nitrogen here. It's very interesting having nitrogen and nitrous oxide in your language because you tend to mix them up. So I'll try to use pressurant and oxidizer because they're a little bit more discernible. You have pressurant here that is going across this regulator and through this particulate filter, and it's the same pressurant that's used for both the fuel and oxidizer. So was a design choice that we made to make it a little bit more realistic for what you might see on an actual rocket or a lander that you might make, because you know, there's very little room to in a rocket to have two tanks of pressurant, even though it technically would be less of a headache. Because then your fuel and oxidizer systems are completely isolated except at the injector. It is kind of a pain having them connected here at this, basically this T right here. But we do this so that we make like kind of a scalable design. So again, we have this nitrogen pressurant going through here. Again, we have that same idea of that this control valve, the solenoid valve, if we want to introduce the pressure into the system. And now the interesting thing here is a check valve exists right here because nitrous oxide, the interesting thing about working with it is it has a propensity to decompose. And when it decomposes, it goes into this, basically it's a chemical reaction where nitrous oxide turns into nitrogen gas and oxygen gas. And the pressure ratio between the before and after of that reaction is 10 to 1. So, you know, if you have 300 psi of nitrous oxide expect 3,000 psi after your system fully decomposes, because that tends to be what the pressure ratio is. So it's important to, if there is a sudden or decomposition of nitrous oxide here, we don't want that to go to the rest of the system. We also just don't want like nitrous oxide vapors to like go into this ethanol system, because again, then you have fuel and oxidizer in the same vessel, and that is a recipe for disaster. So we have this check valve here, and we have some instrumentation here, a pressure gauge, and that manual. Well, this is the pressure gauge. This is the pressure transducer, and it goes across this ball valve. We put this ball valve here because we're worried about introducing nitrous oxide into this system. So this is kind of like a manual way of like, okay, we know that there's not going to be no way for nitrous oxide to leak into here because we manually closed it. And then we have, again, that burst disc here. And now it branches off into two places. I'm going to go, again, for the path of pressure during like a hot fire. You get to this T right here, which branches off for this manual pressure relief with this ball valve here, or it can go across to this flex line and enter this tank. And then this tank, is full of liquid nitrous oxide, liquid oxidizer, and we have a thermocouple here because it's important during the filling procedure to know what the temperature is, and I'll go more into detail about that later. But we have this thermocouple here, and it's reading the temperature. And if it wants to go into the engine, this dotted line here represents that the rest of this system is going to be cut off. You can see that represented right here too. So during a hot fire, this basically doesn't exist. So this is just kind of open to atmosphere. But this ball valve will be closed during a hot fire, and so nitrous oxide will enter, through this control valve. This control valve right here is the final say of like, is there fuel going into or is there propellants going into the chamber, or is there not propellants going into the chamber? So this is like that final like cutoff. The closer you have it to that injector, the more command you have over propellants flowing into it. And if you get closer to the injector, if you command it to go off, getting it closer to that injector will it'll lower the amount of time delay between when you tell it to turn off and when it actually turns off. If you start to include this further and further back in the system, like say for example, if you were to control your flow, you didn't have this like valve right here, but you're only using this solenoid valve 1 here, then there's a lot of like compliance in the system, and so you might tell it to turn off, but the pressure is actually going to go kind of like that. It's not going to immediately shut off, and you get more closer to that effect when you have a valve closer to your rocket engine. And then it goes across the injector, or the check valve into the injector, and there you have that. And so there's a little bit of a lot of things going on here. So going into like the filling procedure, I think it'll be important to talk about kind of a problem that we had to solve, and which is when you have nitrous oxide, it wants to exist as a gas at room temperature. So, how do you get this gas at room temperature down to be a liquid in your tank? You do that by basically cooling your system. So when you have any fluid, its phase is dependent on the pressure and the temperature. So as you can see right here, we have like this nitrous oxide that will change at very high pressures depending on the temperature. So just a 5 degrees Celsius increase in temperature will result in this is like 400 kPa. I don't exactly remember what that conversion was to PSI, but I think it was like 30 PSI, which is nothing to sneeze at, because like, if you think about it, like your car tire is probably pressurized at 30 PSI. So it's a big change in pressure required to keep it as a liquid, depending on like that small increase in temperature. So vapor pressure of nitrous oxide is highly dependent on temperature, but we want to flow these propellants at the lowest possible pressure and the highest possible temperature. And that's because when you get to really high pressures, ratings for your components, they either get they can get very expensive. And when you have like very low temperature ratings that you need for your components, they also get very expensive. So kind of to demonstrate what I mean here is like when we have our tank of nitrous oxide, it's a liquid, but it's at very high pressure because the temperature it's seeing is room temperature. So the pressure in there is like something like 1,000 psi because it's at room temperature. We could just flow it as a liquid at room temperature, but our components would need to withstand 1,000 psi, and that's where things start to get expensive. We could also flow it at, say, atmospheric pressure, but the temperature needed would be cryogenic. It would be like even 200 psi, which is pretty high pressure, but it's lower than what we use. You would be flowing nitrous oxide at like -40 Celsius, which is cryogenic temperatures, and that jacks up the price of components. So we have to find this middle ground, which we decide upon would be 0 degrees Celsius at 600 psi, more or less, something like that. I think it's actually like 580, but we flow it at 600 just to have a little bit of margin there. So how do we get this nitrous oxide down to 0 degrees Celsius and 600 psi? The 600 psi is actually pretty easy. That back pressure regulator that I was talking about before, it controls the upstream pressure of the system. So if we want our system to be at 600 psi, we'll just set the back pressure regulator to 600 psi, and then it can't rise above 600 psi. So that kind of solves that problem. But how do you get it to chill down to 0 degrees Celsius? So initially we thought just to use 0 degrees Celsius is the freezing point of water. So we can just put it in an ice bath, our tank in an ice bath. And that will get the system down to 0 degrees Celsius. So we wanted to use this propellant chiller system that would do that. But wrapping our tanks in an ice bath would kind of be complicated. So we decided to use nitrous oxide as what I call an open loop refrigerant. If you think about how a refrigerator works, it's taking this refrigerant, which is usually butane or something, and it's constantly expanding it and contracting it. When it boils off and expands into a gas, it basically absorbs a lot of temperature or a lot of heat from its surroundings. So you put that expansion boiling off inside your refrigerator to get the temperature down, and then when you have it go across a compressor, it pushes it back down into a liquid, and the fluid will tend to get hotter, right? Or it'll have the temperature, and it will release heat into the system or out of the system. So basically we use nitrous oxide here as an open loop refrigerant. So we have this liquid nitrous oxide, and we have it go into the system as a liquid, and it starts to boil off. And that when it's boiling off and expanding into a gas, it wants to absorb the heat from around the system. And you can kind of see that here, where we have, if you have a fluid here, it's going to absorb heat as it's raising in temperature. And this represents the boiling part of the phase change. So it's able to absorb a lot of heat from the system without changing in temperature very much. So basically, by introducing nitrous oxide as a liquid, letting it go into the system and boil off, it's going to absorb heat from the system. It's going to lower that system temperature, and then we can just exhaust it out the back pressure regulator. As a result of this, we were able to remove that complicated system and introduce what is called thermal conditioning into our process, which is basically just a fancy way of saying that we lower our temperature down to 0 degrees Celsius. So that was kind of wordy, but I'll kind of go forward and explain exactly what that means. So we have this nitrous oxide here, which basically, to kind of give a better picture, this is liquid, and then this is gas here, and this works by having a dip tube here. So the pressure here will basically blow that fluid down in through the straw or dip tube, and liquid nitrous oxide comes out here. When it gets across here, we have this needle valve here because we don't want to just introduce liquid into the system, because that's a pretty high pressure and temperature shock. So we want to use this needle valve to precisely control that flow so that only a little bit comes out through here. And we have this T here, and it goes across this particulate filter again because we want to make sure there's no particulates entering our system in that high pressure oxidizer environment. And then it goes across this ball valve here. Yeah, basically now there's liquid nitrous oxide that is like boiling off, getting the system cold, and getting it's at a high pressure. So you're constantly generating like nitrous oxide gas in here. But that again is being let off by this back pressure regulator up here. So when it gets above 600 psi, after all that nitrous oxide is boiling off and filling the system, eventually it's going to get above 600 psi, which will activate this back pressure regulator and relieve that pressure to make sure that this system is always at 600 psi. So as we're just exhausting and boiling off nitrous oxide, it's cooling the system down to 0 Celsius. And so when it's 0 Celsius and it's at 600 psi, it wants to be a liquid. So then you have liquid starting to trickle into here. And after that point, you can shut off this ball valve here. And now you have a system that's at 0 Celsius, 600 psi, and there's liquid nitrous oxide in here. So that's kind of the fill process here. We also tend to purge the system with nitrogen gas to make sure that there's no atmospheric air in here. Because if you have atmospheric air in a system like this, and you have check valves in your system, those check valves are mechanical. They're like basically mechanical valves that can freeze up. They can lock up if there's presence of moisture that can freeze into ice. Because again, we're cooling this down pretty cold. At 0 Celsius, if not maybe a little bit colder sometimes. So it's important to make sure that there's no water in this system so that you can't get that kind of lockup. Is there any questions about anything that I just said? Cool. So again, we have this P&ID that I was showing before, but how does it actually look in the real life form? So like you can kind of tell the placement of components, but it's really hard to get a sense for like how big things are going to be. So for this, we use AutoCAD because AutoCAD, there's free student license of it, and it was nice to be able to control and like design the layout very quickly. As opposed to using a 3D modeling software like SolidWorks, because that would be kind of like a pain to, if you wanted to redo the design, there would be kind of a headache there. Say, for example, this layout has changed quite a bit, but we, got around that because like the pain to making a new design was much lower because we could just, click and drag things here and there. And not have to worry about mating or things like that. So yeah, we designed this in AutoCAD. This is the ethanol feed system, and the nitrous oxide feed system is here. You'll notice from when I was talking about the P&ID, it kind of seemed like I was talking about it in 2 parts, and that's because it really is 2 parts. So again, we have this ethanol feed system here to kind of follow the path of pressurants. Again, just to relate the 2 together. You have pressurant going through this control valve, it's going across this check valve, and then it goes through this flex line that's not pictured in here because it would be hard to represent a flex line in something like AutoCAD. And it enters into the system and it's able to blow down that ethanol through this this control valve here and out here. One other thing that's like more clear that wasn't maybe very clear in the P&ID, because I kind of forgot to mention it in the P&ID, but it's very clear here, is like there's a path for nitrogen gas to go from here down through this T fitting over through here and actually bypass this ethanol. And we do that because we want to be able to tell the system to flood the combustion chamber with nitrogen gas, basically making a very inert environment at the click of a button. So we can control this valve on or off, and that will sense this pressure and this pressure. Actually, this pressure will be higher pressure than this. So you can turn this off, you can turn this on, and you'll have nitrogen gas flood the system. You can imagine your rocket engines right here. And And when you have, very little oxidizer in your environment, then, that will immediately extinguish the flame because you're getting rid of one of those components of the fire triangle. And that's basically why we chose to do this bypass like that. And, you can see this is where the burst disc would be. This is a ball valve here. This is that solenoid valve that we use to click on and off to immediately relieve pressure remotely. And we have like a gauge here and transducers here. And then nitrous oxide, you can see there's this tank here. Pressure goes in through here. It goes through some instrumentation across this ball valve that I was mentioning before. And then the flex line would go from here to here. It would push that nitrous oxide down. Again, there's that thermocouple that we need to detect when that nitrous oxide reaches 0 degrees Celsius, because then you start to fill it not as a gas, as a liquid, but as a liquid. That's part of that filling procedure process. So we have that thermocouple here, and then pressure would go, or the nitrous oxide when we're actually firing would go across the flex line here into this solenoid valve, across this check valve, and then go into the rocket engine again. So that's kind of our geometric layout. To kind of show what that looks like in real life, well, I'll start with the ethanol actually. It looks pretty similar to our AutoCAD because we designed it very closely to the actual dimensions. Again, you got that pressure going down into here, going through this control valve out to here. Here's that bypass that I was talking about. The safety head, which is our burst disc, and there's instrumentation here. Here's that pressure relief. And then going back to nitrous oxide, again, nothing new here. You have pressure going in through here, instrumentation. Here's that manual relief. It goes up on through that flex line, and that flex line delivers pressure into the tank, and it gets pushed out, into the solenoid valve and then into the rocket engine. So again, that's kind of like our process design, how we went across going from a feed system, P&ID, down to, what you see right here. I really like this skit, kind of shows exactly how things relate. But yeah, this is the test stand that we designed for the 2023 rocket engine. So yeah, we are at the end of the hour. If there's any final questions that you might have.
Yeah, just one. So how do you keep the gas and pressure from flowing around your oxidizer tool? Do you have to keep is it just a vertical thing? Like if it's physically above it, it won't? Yeah,
that's a good point. So the concern is that pressure might go around the oxidizer. Like if we have, it's probably easier to show. It's easier to show here. So if we have this pressure going through this flex line, how does it not circumvent this this ethanol here to go out here? It won't. It will. If you have, think of it like what's a good analogy here? If you have like a straw full of water and you're starting to blow on the top of it, then it will blow the liquid out before it blows the pressure out, which is the air in your lungs. But to what you were saying, you do have to keep the tank vertical for that to happen. You can imagine, I'll actually just go here. If you have a tank like this and your water line or fuel line is like right here, if air is going in here, air is coming out here. There's no reason for it to push pressure in out. So it's important to keep that vertical so that it's actually pushing, that pressure is pushing fuel or oxidizer through the system, and it's not just getting around it. Another important thing is why do we stress having our propellants be liquid is because you only get this blowdown effect if there's a liquid to be pushed down on. For example, if we were to use just like nitrous oxide gas, that would just mix with the nitrogen in the system, and you wouldn't get that blowdown effect. You would get like a mixed effect, and your oxidizer would be a lot less potent. You could also feed oxidizer at as a gas. Maybe you just don't need a pressure for your oxidizer side. You could just get around that by putting a regulator, and that's actually what you see in the USC's system here, they have gaseous oxygen. You know, it's never a liquid. It's always a gas when it's going across here. It's directly connected to the engine. We don't do that because, again, we want to make sure that we can separate these systems out, and you know, we want to have only the right amount of oxidizer that we need for the engine to work for exactly 4 seconds. And you can only do that if you have if you do this blowdown system way. Otherwise, if you just had a small tank of gaseous nitrous oxide that had exactly what you would amount of nitrous oxide you need by mass, then you'd see that pressure start to drop like this, and then then you can't feed pressure at that 600 psi because you're letting out that gas. So it's important for us that we had this blowdown system. Cool. Any other notes or thoughts? Cool. Well, I'll wrap it up here. Thank you for joining, and hopefully this was very helpful. Again, you can contact me if you have any questions about this, even after I graduate. So